Good evening. So this is yet another one of those sections in which I took some time before we started to sketch this, and then I'm going to explain it while you should try to actually do the same thing on your notes to sketch it while you listen to me. So the application in this section is to to establish a formula that computes the surface area of given by a function of two variables. So the surface area given by a function z equals f of xy. So in red here, let's imagine that this is how the surface looks like, right? And over a certain domain. Now remember, if you just do the double integral, that is going to represent the volume between the graph of the function and the domain. So what we're trying to do today is analogous to calculus 1. Again, it's always useful to make some sort of analogy. In calculus 1, remember, if you had a function of a single variable, just the integral, right? Let's say this is the graph of the function. Just the integral would be the area between the graph of the function and the x-axis. Now, analogous to what we're trying to do today is to devise a method to compute. In calculus 1, there was an integral designed to compute the length of the curve that represents the graph, or the arc length. So the length of f of x, right? Which in calculus 1, remember, it was the same integral, the same bounds, but the integral of square root of 1 plus f prime of x squared. We met this formula actually in some fashion when we talked about space curves, which is basically that's the magnitude of the tangent vector. It's what you integrate to find the length of the curve. So analogous to this for a function of two variables is to find the surface area represented by z equals f of xy. So as always, we're going to start with a partition. So again, to speed up the process, we're not going to sketch the whole domain and the Riemann sum. We're going to basically establish what the limit of the Riemann sum will look like for the purpose of computing the surface area. But let's notice one important thing, right? So once we make this partition in the domain, what I wrote here on the bottom here, dx dy, basically it's a piece of the partition after we take the limit in the Riemann sum. And so that means the sides of the partitions are dx and dy. Oh, by the way, just going back again to calculus 1, you could visualize the way we actually derive that quantity 1 plus f prime squared under the radical by looking at the a piece of the graph corresponding to a change in x, to a change in y, and approximating in that case the length of the graph with the actual slope of the tangent. Right? The tangent, which is viewed here like a hypotenuse of the right triangle given by dx and dy. So in other words, from Pythagorean theorem, you approximate the piece of the arc length by square root of dx squared plus dy squared. But then remember, because y is a function of x, dy was f prime of x dx, that's the differential, right, of f of x. And then if you plug it back into the radical and move dx on the outside, then you get the piece to integrate, which is square root of 1 plus f prime squared dx. So we're going to use a similar analogy here, but let's see how we connect it to the area. So going all the way back to the three-dimensional picture here. So for a piece of the partition, we're going to have a piece on the surface of the surface that we try to compute. So here with red, I'm representing the piece of the actual surface that we're trying to compute. And because dx and dy is very small, we can approximate that piece with a planar tangent plane, or a portion of the tangent plane given by, in this case, a parallelogram. So basically, we try to come up with a parallelogram coming from the tangent plane at this point, which will eventually approximate the area of that piece of the surface. So the plan of attack is to approximate the red portion, which is the actual surface, with a planar figure given by, it is in green, given by that parallelogram. So bottom line, what I need are actually two vectors corresponding to dx dy that form this tangent plane. Let's call this vector u over here along the x-axis, and this one v bar. And let's remember also from previous sections that the area of the parallelogram is actually the magnitude of the cross product of the vectors that define that parallelogram. So I hope the analogy is more or less clear, right? I mean, from approximating an arc length with a straight line, here we're approximating a patch, a portion of the surface with a tiny parallelogram. Okay, so what are the components of those vectors actually? Because again, remember, intuitively in the limit, these are obtained by making a small change in x, small change in y, and a small change in z, right? It's analogous to calculus 1. If you view, for example, if you keep y constant, and you view what happens to u bar, right, over there, you can view that also in a triangle that involves the z and the x coordinate. Kind of like this, that vector u is basically with a vertical component given by a change in z, and a horizontal component given by the change in x, again as y is kept constant. And the actual curve is, I mean, this is the portion of the surface corresponding to that situation when x is constant. And then we're trying to figure out basically a vector with these components. This is the vector u that I'm trying to establish here, with the components basically given by dx, dz, and, well, 0 for y, because y is a constant. So the components of u, again, from the beginning, it's going to be the change in x, that's the x component. The y component is 0 because y is kept constant, so this vector is going to be parallel to the xz plane, right? And then finally the third component is the change in z. Okay, so the components of u and v again result from a tiny change in x, y, and z. But again, if y is constant, then that component is 0. Also, because y is constant, you can view z as a function in x only, which means dz is simply the derivative with respect to x, which is partial x, times dx. So the vector u is dx 0 partial x of f dx. And I hope it's pretty clear at this point, analogously, the vector v, which is when x is constant now, well, the x component is going to be 0, right, because it's parallel to the yz plane. Change in y is the y component, and because you can now view the function as a function of y, the change in z is going to be partial y and then dy. So the vectors that define that tiny planar parallelogram, I mean that tiny parallelogram that approximates the patch of the surface, are given by this vector u and v. What we integrate to achieve the area, because again, the idea is that you come up with a Riemann sum. You're going to add up all these patches, which is to say you have a double Riemann sum over the domain, and then in the limit leads to a double integral. But what we integrate is not the function itself, but the cross product given by these vectors. So what is the cross product? Well, let's write down again the symbolic determinant here. Dx 0 fx dx 0 dy fy dy. And then the first component is going to be minus partial x, let's see, 0 dy, minus partial x dx dy. I mean, the order of integration is going to be established in the actual problem, obviously. The middle term is dx times fy dy minus 0 with a change of sign, so it's minus fy dx dy. And finally, the third component is just dx dy. So the area of the parallelogram is the magnitude of this cross product. So therefore, the surface area, and then let's actually, I mean, if you write down the magnitude, that's going to be, yeah, let's just write the formula on the next page. So the magnitude of u cross v is going to be square root of fx squared dx dy squared. That's going to come out of the radical, obviously, plus fy squared dx dy squared plus dx dy squared. So if you take it out of the radical, this dx dy, and we're going to start with the last term here, that's just 1 plus fx squared partial y squared dx dy. Okay, so this is the piece to integrate that gives you the surface area. And I hope you see the analogy with calculus 1, or with the arc length if you want, when you have just 1 plus f prime squared. It's a very similar formula, except that this is for a double integral, and the meaning is the surface area. So we're going to write the formula on the next page, and then we're going to continue with a bunch of examples. Okay, so this is the formula, and let's go over an example. By the way, dx dy is dA because we use the Cartesian coordinates in the derivation of the formula, but obviously you can change that to polar if you think it's suitable, as it will be actually in the following problem. So in my first example, let's find the surface area of the inverted paraboloid z equals 4 minus x squared minus y squared above the xy plane. So we need to establish the domain first. Sometimes you don't need to sketch, but in this case it's useful to maybe sketch it a little bit like that. So a paraboloid open downward is going to cut the xy plane, and we're going to have to compute that intersection. So obviously when z equals 0, which represents the xy plane, 4 minus x squared minus y squared equals 0, which means the domain is going to be the disk given by x squared plus y squared equals 4. So that is the domain D of the double integral. And again, it's useful, not so much in this case, but it's always useful to take the domain apart and sketch it in a two-dimensional system, because especially if you have to do Fubini theorem in Cartesian coordinates or even in polar coordinates, it's better to visualize the domain clearly in the plane here. So that's a circle of radius 2. So let's call the function f of xy as well. It's not necessary, but in the beginning let's just do it like that, with one step at a time. So the surface area then is going to be the double integral of square root of 1 plus partial x squared plus partial y squared. Obviously carefully write down what that means before you decide how to compute it. Okay, so partial x of f is minus 2x squared, and then partial y is minus 2y squared. And by the look of it, it's pretty clear that I'll probably use polar coordinates, right? Because of the shape of the domain and the stuff to integrate, because it involves x squared plus y squared. In the domain, in the polar coordinates, the domain is a full disk. So I hope you know the drill by now. The outer bounds are for theta, which are from 0 to 2 pi. Inner bounds are for the radius, which run from 0 to 2. The stuff to integrate is 1 plus 4r squared under the radical, because x squared plus y squared is r squared. And don't forget the extra r, when you replace dA with r dr d theta. This is suitable for a u substitution. And the new bounds of integration are when r is 0, u is 1. When r is 2, u is 17. Again, just like previous examples, we can pull out the integral in theta on the outside, and then the remaining integral is from 1 to 17 square root of u, which is u to the 1/2, and r dr is d over 8. First integral is 2 pi, and then 2 over 3 u to the 3/2 between 1 and 17. Number simplification here, it's 1 over 12. I lost something here. 1 over 12 times 2 pi here, right? So there's a 2 pi over there. 1 over 12, 17 to the 3/2 minus 1. So it's pi over 6, 17 to the 3/2 minus 1. Okay, so usually, I mean, we're going to go over other examples. As we move along with these tools, it's more and more important to pick the right tool, okay? It's often people make, and that's, again, this is a message to my students watching this. Critical to see what the problem is asking, you know, because, for example, many people rush and then set up the double integral of the function itself. And that's not what we ask in the problem, right? We ask the surface area, which is given by the integral of square root of 1 plus fx squared fy squared. So if you start with the wrong integral, it's very difficult to give partial credit, especially if the intermediate steps are far different in terms of, you know, difficulty, for instance, you know, and then, you know, you don't want to. So bottom line, just take your time and read the problem carefully. All right, so let's continue with a couple of more examples. All right, so here's an example that for which you don't need to sketch anything, which is good because it's not exactly, you know, simple thing to do. So find the area of the plane, the portion of the plane given by 5x plus 3y minus z plus 6 equals 0 above the rectangle given by 1, 4 by 2, 6. So remember, this is a notation for a rectangle. What it tells you is that the bounds for x are 1 to 4 and the bounds for y are 2 to 6. So you don't need to sketch anything because essentially the function is given, the domain is given. So however it looks like, that's going to be it. You do need to connect it with the tool at hand, right? We have a formula for the surface area given by a function of two variables, z equals f of xy. So that means it's your job to view the plane as a function of two variables. That is to say, you get z by itself, and then z is going to be 5x plus 3y minus 6. So that's the equation of the plane given in the problem as a function of two variables x and y. Planes are basically as good as lines in terms of calculus. It's all linear, so derivatives are quite nice and simple. So let's just set up the integral right away. The surface area is going to be the double integral of 1 plus, once again, partial x squared, partial y squared. This is an integral of a rectangle. The order of integration doesn't matter in terms of, I mean, you can write it in any order you want. So from 1 to 4, 2 to 6, and then 1 plus partial x is 5, so 5 squared, partial y is 3, 3 squared, and then dy dx. So it's pretty straightforward because this is just a constant, right? So basically you can attach it to y or x, whichever you prefer. It's still a product of two integrals because you can view it as a product of a function in x and a function in y, except that both functions are constant. You can, for example, say that it's 1 dx times from 2 to 6 square root of that quantity, which is 25 plus 9 plus 1, that's 35 dy. Or you can just move root 35 out of the all integrals to begin with. So the antiderivatives are x between 1 and 4, root 35, y between 2 and 6. Root 35, 4 minus 1, 6 minus 2. Or you just remember this is essentially a box. So the volume of a box is the product of the dimensions of the box, right? Root 35 is the height, 4 minus 1 is one side, and 6 minus 2 the other side. So 3 times 4, that's 12, square root of 35. And this was the second example, right? So my last example is one in which you only need to sketch the domain. Again, only sketch by hand whatever you need, not more, because often the actual shape of the surface could be quite difficult to sketch by hand, as it is the case pretty much all the time, with some exceptions. So let's find the area of the surface given by z equals 1 plus 3x plus 2y squared. So this is my function of two variables representing the surface, but only the portion of it above. See, when it says above, that means the domain is already given to you. So above 0, the triangle given by the points 0, 0, 0, 1, 2, 1. So here we have to spend some time actually sketching that domain before we jump to the integral. So, I mean, not a lot of time, but some time, right? Okay, let's see the points that define the triangle, right? So 0, 0 is the origin. 0, 1 is over here. So let's say this point is 1 over the y-axis. And 2 and 1, which is over here. Okay, so this is the domain in question. Obviously, I can use Fubini theorem by treating this either as a type 1 or type 2 domain, whichever you prefer. In both cases, we need to find the equation of this line, right? So, I mean, we need, let's say I want to view it as a type 1 domain. As a type 1 domain, then I go with the outermost integral by x. So I know that x is between 0 and 2. That's pretty obvious. But then I need to figure out the bounds corresponding to a given x in terms of x. So the bounds for y in terms of x. Now the upper bound for y is clearly 1, right? That's obvious because it's a horizontal line. But the lower bound comes from the equation of the line connecting 0, 0 and 2, 1. So you have to take some time here to find the equation of the line connecting 0, 0 and 2, 1. So the slope of this line is 1 minus 0 over 2 minus 0, which is 1/2. And then from the point slope formula, using the origin, for example, we see that the line is y equals x over 2. So that means the lower bound is going to be y equals x over 2. And with that, we are ready to set up our integral. Let's set it up directly as a type 1 integral. So 0 to 2 on the outside for x, and from x over 2 to 1. And what do we integrate? We integrate 1 plus partial x, which is, let's see, 1 plus 3x plus 2y squared. 1 plus partial x, which is 3 to the power 2. and then partial y, which is 4y, again raised to the power 2. And then in the order dy dx. In the order dy. Oh, that's actually, yeah. we're not going to do it in this order, but actually that's actually a very good opportunity to comment on this, to reinforce why it's so useful to be able to change the order of integration. So here's the thing. Yeah, I forgot about that, but see, this is actually a good experiment. See, let's actually see what we get here, right? I mean, it's possible, but it's actually better to go the other way around, right? So if I simplify this, what I have to integrate is 9 plus 1, which is 10, plus 16y squared. Now, those of you who remember calculus 2 stuff, you might remember these are not exactly simple integrals. It's doable, but it's extremely tedious because this requires a trig substitution. And not to mention, who knows what you get after you plug in the bounds given in terms of x for the next integral. So this is the moment when you should see, if you treat this whole thing as a type 2 domain, whether the integral actually might be easier to compute or not. So this is too hard. Okay, let's set it up as a type 2 integral. That means I go by the y first, so look at the horizontal slice on the domain. So as a type 2 function, y is between 0 and 1, so that's going to be my outermost integral. And then x goes from 0, the leftmost bound, all the way up to whatever x is equal to from the equation of the line. So again, going back to the equation of the line, the x in terms of y is going to be 2y. So the same integral now is going to be from 0 to 1, and then from 0 to 2y, same stuff to integrate, 1 plus, or 10 plus 16y squared, dx dy now. Now, does that make a difference? Well, first of all, the innermost integral is trivial now. It may not look like that, but it is trivial because in terms of x, that square root is just a constant, so I can pull it out of the radical. And then you're left to just integrate 1 dx. Now, 1 dx is just x, right? Between 2y and 0. That ends up being 2y minus 0. So the innermost integral is 2y multiplied by that constant. I mean, the innermost integral is 2y times this square root, right? And then the last integral is this in terms of y. Yes, it does make a difference because now instead of trig substitutions, which are too hard, are harder in general or more tedious, now this whole thing is eligible for a u substitution because you have the extra y on the outside. So I can make u to be 10 plus 16y squared. Du is going to be 32y dy. The bounds of integration are when y is 0, u is 10, and when y is 1, u is 26. Okay, so now my integral becomes from 1 to 26. Integral from 1 to 26. So when u is 0, what is the second? No, sorry, not 1, 10. From 10 to 26. Right, u from 10 to 26. Okay, and then the square root becomes square root of u, so it's u to the 1/2. There's a 2 over there, so that I won't lose. And then y dy from the substitution becomes 1 over 32 du. Okay, so the constant that comes out is 1 over 16. And the integral u to the 1/2 is 2/3 u to the 3/2 between 10 and 26. So this will be 1 over 24 constant, and then quantity 26 to the 3/2 minus 10 to the 3/2. Okay, so I think that's enough for today. Let's see, this is what comes next. This is 15. I forgot what comes next. Yeah, so we're gonna go to the triple integral pretty soon. I think the next topic, if I'm not mistaken, but we'll see. So that's it for today. I'll see you next time.